just get some more practice looking at Lewis structures and just trying to figure out structure. So how about the A? What's the angle you predict for A? 120. This is trigonal planar for both EPG and MG. B, 109. This is going to be tetrahedral, both MG and EPG. C, 109. This should be tetrahedral EPG, which is going to set the angle 109. And it's going to be, what's the shape of this going to be? Yeah, that's right, trigonal pyramidal. So let's take a look. So here we can see the trigonal planar arrangement of the atoms here around this carbon. This carbon is going to be tetrahedral. Here. 2 carbon-carbon single bonds and 2 carbon-hydrogen single bonds. This one's going to be trigonal pyramidal. There's lone pairs sticking out on the other side. Do you see it? And so they just twisted it. So the pyramid, the base of the pyramid is facing us. It's trigonal pyramidal. Again, these bonds can twist. You know, single bonds can twist. And so this whole thing can twist around like this. Double bonds are not capable of twisting. So this is pretty rigid here, but this is flexible here. So what we try to do is we try to flatten it out, draw as many atoms as possible in the plane. So this would be the zigzag here, all in the plane. Which are polar? Oh, actually, I guess we did that. Did we do these?
Yeah.
Okay. BF3 is going to have a trigonal planar structure. Would you expect it to be polar or non-polar? Non-polar. NH3 is a trigonal pyramidal structure. Polar or non-polar? Polar. Because the trigonal pyramidal is not going to cancel each other out. And this one, GH4, has a tetrahedral structure, and so that should be non-polar. Describe the shapes. The shapes are just, you know, whenever we have 2 atoms, no matter what, it's going to be linear. And so HF is linear, HBr is linear. Which one's more polar? Well, HF is going to be more polar than HBr. Why? Yeah, fluorine has much higher electronegativity than bromine, so it's going to pull more. The hydrogen end of each is more positive. The fluorine and the bromine are going to pull the electrons. Sketch the Lewis diagram for the water molecule, paying particular attention to the bond angle, using arrows to indicate the polarity of each bond, and sketch the methanol molecule, again using arrows to show bond polarity. Predict the approximate shape of both molecules around the oxygen atom. Also predict the relative polarity of the 2 molecules and explain the prediction. All right, so let's take a look at the Lewis structure. You know, carbon, when we look at this part here, you know, carbon and hydrogen have pretty close electronegativities. And so, you know, both of these are going to be about the same in terms of polarity. Actually, let's draw these ones out over here. So if I draw oxygen, what I like to do is I like to draw, you know, tetrahedral, I like to draw the bonds in the plane. That leaves the lone pairs out of the plane. Like that. So this would be my tetrahedral arrangement of bonds. Then I look, you know, I know that, what's this arrow called? The green arrow is called a?
The dipole?
Dipole. Okay. It's a dipole. And so these 2 dipoles are going to end up with a net molecular dipole pointed which way? Well, if this one's pointed in, then we're going to get a net molecular dipole like this. So this would be the molecular dipole. little bit bigger than it should be. That's it. Now, if we compare that to something like methanol, methanol is very similar. It's very water-like in this part of the structure, at least. It's just that instead of having a hydrogen there, we have a CH3 group. Do you recall what we call the CH3 group? What's that called? CH3 group is called oxalate is C2H, no, C2O2. C2O2 2 minus. Oxalate, C2O4. Oxalate is C2O4 2 minus. What's the CH3 group called? CH3. CH4 is methane. How about what's the OH group called here when it's in an alcohol? What's that called? The OH group. Alcohols have this group attached to it. It's the COH, and the OH group we called, not hydroxide, we called it something else. It is an alcohol, so you got alcohol, but it gets a name in organic chemistry. Hydroxyl group. So hydroxide, it makes a hydroxyl group. What do you think methane? This is kind of like methane, except it's missing a hydrogen. What do you think this is called? Methyl. Methyl. If you recall dimethyl ether, what did that look like? Dimethyl ether had two methyl groups, CH3, CH3. This is also called methyl alcohol because it's a methyl group attached to an alcohol. And so methyl alcohol or methanol, those are two names for this. Ethyl alcohol or ethanol, with ethyl group CH3, CH2. I don't know if you guys caught that, but I mentioned it the other day. Anyway, the carbon is about the same. It's just slightly more electronegative, but and so carbon's slightly more electronegative than hydrogen, but it's not dramatically so, and so that it's comparable. And so the net molecular dipole kind of looks similar, be coming off like this. And so the two molecular dipoles are very comparable. This is why methyl alcohol and water mix easily. If you have methanol and water, they mix in all proportions. Like this. If I had a bucket of water, how much water can I add to a bucket of water? Is there any limit to how much water I can add to water? No. And so water likes water, and so you can mix it together. It makes sense. This, what we call miscible. Well, methanol is the same way. How much methanol can we add to water? There's no limit. We can add as much methanol as we want because methanol likes water. Water likes methanol. I could add as much water to methanol as I want. There's no limit. However, some things do have a limit, like how much oil can I add to water? Not much, because it'll separate. Type of thing. Which have tetrahedral shapes? Which species have tetrahedral shapes? Well, when they're saying shapes, are they talking about the EPG or the MG? What do you think? Yeah, if they're talking about the shape, they're most likely talking about the MG. So what would you say that is? Well, we could name the shapes. This would be tetrahedral. This would be bent at what angle? 120 or 109? 109. This would be trigonal pyramidal. Angle should be 109. B, well, let's look at ABC. Okay, B is going to be polar. C is going to be polar. Because it doesn't have that symmetry where everything cancels out, you know, where it's bent. This, if you look at this, this should be non-polar. However, it's an ion, so ions are polar. They're monopoles, not dipoles. They got negative charge. And so it's non-polar in the sense that it's symmetric. It's that spherically symmetric, but it's polar in the sense that it's a monopole ion. The same thing, this is, what's the shape of this? Tetrahedral. So you'd expect this to be non-polar, but it's an ion, so it's got a pole to it. It's got a positive charge to it. The dipole has a positive and a negative end. The monopole is just going to have a positive or a negative, like the top one. How about this one? What's the shape of this? What is it? Linear. This is going to be linear. Is it going to be polar or non-polar? Non-polar, no, because it's equal and opposite poles. What shape is this one here? True, no. Planar. Is it polar or non-polar? Non-polar. Non-polar is because if you have a three-way tug-of-war, you know, is one of these fluorines stronger than the other? Let's say this fluorine's stronger than these two, so it's going to pull this way. If you have a three-way tug-of-war, you know, and everything's at 120 degrees apart, then basically they're all going to cancel each other out. You could try it, you know, at home. Put everybody at 120 degrees and see, you know, if there's going to be a winner. If everybody pulls with equal strength, you know, there's not going to be a winner in this tug of war because it's spread out evenly, and so therefore, you know, you can't say these two are stronger, so it's going to pull this way. You know, you got to think if it pulls in any direction, that means that direction is stronger. And so how can it be stronger if they're all the same? It's kind of weird because it's not, you know, it's three ways, so you have to think about it, but a three-way like that is. Those are multiple choice. What distinguishes an organic compound from an inorganic compound? Yeah, they're organic compounds are carbon-hydrogen-based compounds, typically. Some organics don't contain hydrogen. Some inorganics contain carbon. So there are, you know, some exceptions. But it's basically carbon-based compound. All organic compounds contain carbon. Inorganic compounds can contain the rest of the periodic table and sometimes carbon. What features of the carbon atom account for its ability to form so many chemical compounds? The reason why organic chemistry was split off is because carbon forms so many different chemical compounds. Why? I mentioned this verbally. I just said carbon can form up to how many bonds? Carbon can form up to 4 bonds. So it can form a lot of bonds, and carbon doesn't mind forming chains. Right? So it can form chains. Not only can it form chains, it can form rings, like we saw earlier. There's no problem with that. You know what this is? Is that hydrocarbon, alcohol, or carboxylic acid? Do you recognize what what is CH3 called? That's methyl. This is methyl alcohol or methanol. And so this would be an alcohol. How about this? This is a compound of just carbon and hydrogen, so that would be called a hydrocarbon. So this is a hydrocarbon. This is 8 carbons, so this is called the hydrocarbon called octane. Octane means 8 carbon hydrocarbon. Octane. This is actually a ring of 6 carbon atoms, but this would also be a hydrocarbon. This is called benzene. I think at the gas station, if you see, there's a little warning sign about benzene in gasoline. It says benzene in gasoline. C6H6. Is this a hydrocarbon? CH2NH2? 2? No. This is a different kind of organic compound. Do you know what this one's called? We did 2 of them yesterday. I don't know if anybody wrote it down. C2H5NH2 was one of them, right? Does anybody remember what I called that? Glycine was the other one, the second one we did. The first one we did. The second one, what did I call that? It's glycine, which is part of what family of organic compounds? Or let's go back to the first one, the C2H5NH2. Did anybody write down the name of that? C2H5 I called ethyl. It was ethyl. Well, I guess nobody wrote it down, but it was called ethylamine. This is called an amine, A-M-I-N-E, amine type organic compound. It has nitrogen, carbon and nitrogen, hydrogen. Those typical amines. These amines are also part of the amino acids. Amino acids consist of an amine and an acid. Amino acid. The first part of the amino acid, glycine, we wrote as the amine, and the second part was the acid. Glycine was one of the simplest amino acids. How about this one, C8H18? Hydrocarbon, alcohol, or it's a hydrocarbon. A lot of amines are also drugs. Let's take a look back here. Aspirin, well, this is acetylsalicylic acid, is carboxylic acid. Do you see it? COOH. This is also called an ester. There's an ester here, which we haven't talked about at all. It has this type of link. It's like an acid. It's carboxylic acid, aspirin. Lactic acid, well, that's obviously going to be an acid, lactic acid. COOH, carboxylic acid. Cinnamaldehyde looks pretty much like a hydrocarbon. It's got this ring though. This is kind of a benzene ring. This is what a benzene ring looks like, but it has hydrogen in there. It's got a lot of double bonds in there, but this is called an aldehyde here. COH. COH is an aldehyde. It gives us, these groups give it different properties. Amphetamine, we got the the carbon hydrogen stuff going on here, but what's that? That's an amine type group there. The N, do you see the NH2? So we got nitrogen, it's like ammonia. So when we got nitrogen in there, that could be an amine. If it's nitrogen bonded to hydrogen or carbon, it would be an amine. And so amphetamine is an amine. A lot of drugs are amines, actually. And so amines are an important class of organic compounds. Talk about that many amines. Hydrocarbon and carbohydrates are similar terms. Both are made by combining word parts. Carbohydrates are interesting because of the ratio. Like for example, sugar, table sugar. Do you know the formula for table sugar? C12H22O11 is the formula for table sugar. What's the hydrogen to oxygen ratio in table sugar? Look at the hydrogen to oxygen ratio. 2 to 1. Do you know that all carbohydrates have a hydrogen to oxygen ratio of 2 to 1? And hence the name, carbohydrate. But you know, carbohydrates don't contain water. This has got a ratio of 2 to 1. And so all carbohydrates have that ratio. You aren't going to find any water molecules in sucrose, so this is sucrose. If you want to look at what sucrose looks like, let me pull up the structure here. This is a molecule of sucrose here. This is trying to show wedge dash, you know. You see the wedge dash? Business going on here. This is flat, this is a planar ring, this is also a flat ring too. This consists of a glucose and a fructose linked together like this. I don't see any waters in there, but it's got a 2 to 1 hydrogen oxygen ratio. Sucrose. Distinguish between the structure of an organic molecule as given by its Lewis diagram and the three-dimensional shape of the molecule. Are they the same? Lewis structure and three-dimensional shape? No. The structure of a molecule simply describes in 2 dimensions the relative position of how, you know, the Lewis structure just shows how the atoms are connected. The three-dimensional shape, which is that wedge and dash diagram, shows the orientation of those connections spatially. In other words, the shape of the molecule. We use wedge dash diagrams to show molecular structure and molecular shape. What's the difference? Molecular structure and molecular shape, that's the same kind of thing. 61, why can a zigzag chain of carbon atoms be drawn as a straight line in the Lewis diagram? Why can a zigzag chain of carbon atoms be drawn as a straight line? Because Lewis diagrams don't care about the shape. They just want to show the connections, that's all. There's another reason, and that is, if you look at the zigzag line, it depends on your perspective. If I look at this zigzag line here, let's look at this zigzag line here. If I look at it from the side like this, I see the zigzag. But what if I look at it from the top? If I look at it from the top, it looks as if it's a straight line, you know, because I don't see the zigzags, right? And so it depends on where you're looking, you know, your point of observation. If your point of observation is from the side, yeah, sure, you're going to see the zigzag. But if you look at it directly from above, all you're going to see is a straight line. Unless you have some shadows in there. Well, let's see what their answer is. A straight line in the Lewis diagram simply indicates that atoms are bonded together. We don't show any shape. What is the condensed structural formula? Condensed structural formula, do you know what that is? We talked a little bit about it. Why is it useful in drawing Lewis diagrams? Well, the condensed structural formula would be like this. You know, the two ways I could write out methanol, I could write it CH3OH. And so I could just condense the structure down. Here's my CH3, here's my OH, CH3OH. Or I could write this properly, you know, CH4O. This would be the proper molecular formula. which one is more useful? CH3OH, the condensed structural formula, or the molecular formula, CH4O? When you see CH4O, do you see methanol? No, I don't. I don't see methanol at all. But when I see CH3OH, oh, I see methyl alcohol, methanol. No. And so a condensed structural formula will give you clues as to how things are bonded. How are alcohols and ethers similar to water in structure and shape? Well, you know, here's water. Here's an alcohol. And an ether, what's the difference? An ether is going to have another carbon bonded here. So if you look at dimethyl ether is going to have the same kind of shape, except rather than, you know, if I look at this, I'm going to put the two methyls here. Same shape around oxygen. So we'll go like this. So the polarity is going to be about the same because carbon and hydrogen are pretty close, you know. And so if I just knock off another hydrogen and replace it with this, you know, it doesn't really change the bond dipole that much. So it's still pulling towards oxygen, just not as big. Still going to put something like this. So this is dimethyl ether. Name and describe the group that is present in all alcohols. What's the name of the group that's present in all alcohols? You just told me not too long, or I told you and then you told me. What's it? Hydroxyl. Hydroxyl group is present in all alcohols. What does it look like? It's a COH linkage. What does the presence of this group contribute to an alcohol molecule and its properties? Well, it's going to contribute to polarity for sure. That's a physical property, you know, it's polarity. This means that water and alcohol, these alcohols are quite light. Methyl alcohol is what we say miscible. It mixes in all proportions with water. It's the same thing with ethyl alcohol, propyl alcohol. But when we get to butyl alcohol, that is when we have 4 carbons in this chain, butanol is barely soluble in water. Butanol doesn't like water because butanol is becoming more and more hydrocarbon-like, like gasoline. Like gasoline is a mixture of hydrocarbons, mainly. And the alcohol, you know, these have certain chemical properties that you associate with alcohols. The chemical properties aren't going to dig into that deep. Yeah. Most alcohols are combustible. How do carboxylic acids differ from other acids such as hydrochloric, sulfuric, and carbonic? Carboxylic acids have what group? The COOH group. So carboxylic acids contain the COOH group. Do you know what that group is called? It's called the carboxyl group. What are carboxylic acids? Identify the group that is present in carboxylic acids. So this is repeat COOH group, carboxyl group. Write a Lewis diagram for the group and describe the geometry. We already did that yesterday, right? What was the geometry around the carboxyl group? Trigonal planar, correct. This is a trigonal planar group. So the carboxyl group is going to be, let's say, here, it's the COOH, right? And so we're coming in, here we hit the COOH. So when we look at this carbon, it's trigonal planar. However, this oxygen is not trigonal planar. This oxygen is bent. And so this is trigonal planar bent. But, you know, they're talking about that carbon that they're referring to in this particular question, but there are two central atoms in this, so we do them each individually. Distinguish precisely and in scientific terms the differences between the central atom and terminal atom. This one has two central atoms. Each central atom we have to do. Central atom bridges atoms. Central atom, central. Hydrogen is a terminal atom. Like that there. Molecular geometry and electron pair geometry. Yeah, molecular geometry is the shape of the atoms. And what is electron pair geometry? Not the number of bonds, it's the shape of the electron groups. So electron pair geometry is the shape of the electron groups. Like the shape of the electron groups here is tetrahedral, but the molecular geometry is the shapes of the bonds, which is, what is the shape of this one? Bent. Bent or angular. Angular is another name for bent. What's the difference between bent and trigonal planar? Well, that obviously look different. Trigonal planar and trigonal pyramidal. These should be really obvious. Trigonal pyramidal versus tetrahedral. No. Totally different shapes. Polar versus non-polar. Polar means unequal charge distribution, unequal electron cloud, that kind of thing, over the entire molecule. Polar means it's symmetric. There's no net dipole. Polar molecule will have a net dipole, non-polar will have no net dipole. Classify each of the following as true or false. Molecular geometry around an atom may or may not be the same as electron pair geometry. True. Electron pair geometry is the direct effect of molecular geometry. False. Why? It's the opposite. Electron pair geometry affects the molecular geometry. If the geometry of a molecule is linear, the molecule must have at least one double bond. False. A molecule with a double bond cannot have a trigonal pyramidal geometry around the double bonded atom. False. Yeah. It's because our book doesn't expand the octet. That's the reason why. So it depends on how you do chlorate. If you do chlorate, well, chlorate is not the best one thing to do. It depends on if we expand the octet or leave the octet. So if we expand the octet, then this would have to be trigonal pyramidal with double bonds. Expand the octet. So now, it's false. It's because they restrict it to not expanding octet. This is not a good question. Also, it's not so easy to expand the octet, especially like having two double bonds on chlorate, because of how the double bonds form. How the double bonds form, we aren't really talking about here. And so let's discuss more in Chem 1A. But if we look at the structures online, you'll see most of the structures here will have two double bonds and a trigonal pyramidal structure. But the reality is these Lewis structures and resonance, this kind of stuff and that kind of stuff is not the best way of describing these ions and molecules. Do you know what the best way of describing these ions and molecules is? This is, I call the quantum mechanics light version. Do you know what I call the quantum mechanics full version? Give it a name. Here, wrote it on the board. This is in relation to O2. You go way, way back and look at O2. The question was, what is the full, this Lewis structure, Vesper, etc. We use a simplified version of quantum mechanics to figure out. Because of that, we end up with a problem. For example, here it was discussed in this expressional shape, discussed in chapter 12. So I talked about it at this point. Oxygen, it is impossible to write a single Lewis diagram that satisfactorily explains all the properties of molecular oxygen. So if we can't write a Lewis diagram, in other words, a Lewis diagram for oxygen is wrong. And so does that mean, well, it's wrong? Well, what happened to the Bohr model of the atom? The Bohr model of the atom was wrong. And so what happened to the Bohr model? Well, we disbanded. We pretty much disregarded the Bohr model, right? We didn't pay much attention to orbits. We looked at orbitals instead. Well, if the Lewis structure of oxygen is wrong, then all this drawing these Lewis structures is a waste of time, right? Because it's giving us the wrong answer. And so why are we doing it? Why don't we use the proper theory for this? Well, it turns out the proper theory is a bit too complicated, and there aren't that many exceptions. So we're just going to live with these techniques for drawing Lewis structures. And if you wanted to get a more accurate picture of what's happening with oxygen, we would have to use the full version of quantum mechanics, which is called molecular orbital theory. What we're doing right now is something called valence bond theory, which is a partial or light version of quantum mechanics. And so the same thing happens when we look at this. This is not really totally accurate, nor is having the octet totally accurate. It's something of a, we have to really apply molecular orbital theory to get the best picture of what's going on with these. And molecular orbital theory is the full quantum mechanical treatment. Okay, that's good. That's the connection. You might be wondering, what is this molecular orbital theory thing? Well, that's what it is, but that's what it is. A CO2 molecule is linear, but an SO2 molecule is bent. CO2 is linear. SO2 is bent because it has a lone pair here. You'd have to draw the Lewis structure to figure it out. A molecule is polar if it contains polar bonds. True. It's false. False. CO2 contains polar bonds, but it's non-polar. Why? CO2 has very polar bonds. The carbon-oxygen bonds are very polar. But the molecule itself is non-polar because these polar bonds do what? They cancel each other out. And so this is false. we can have a nonpolar molecule with polar bonds. A molecule with a central atom that has one lone pair of electrons is always polar. Our book says true. But it depends on the bonds. You know, if the bonds are nonpolar, then even if it has a lone pair there, regardless of the shape, if the bonds are nonpolar, then but go ahead and follow this rule. And so if we have the book has an easy thing. If there's a lone pair present on the central atom, it's going to be polar. And so you could just use that. I'm not going to throw in anything different. A molecule with a central atom that has two lone pairs and two bonded pairs is always polar. Your book will say
That's true.
but, you know, they qualify it. If central atoms are limited to the 4 electron pairs as they are in this book, and so they're limiting this, but this is wrong. This is wrong. That's all right. Now this follows from the previous statement. If there's a lone pair, then it's polar. There's a lone pair, therefore it's going to be polar. Just remember that. Remember, sometimes our book oversimplifies things. So when we get for Chem 4, you're okay here, but as you go on, you might have to look at these molecules in more detail structurally, but it's all right. Carbon atoms normally form 4 bonds. It's true. Hydrogen atoms never form double bonds. That's true. One kind of C6H12 molecule has its carbon atoms in a ring. Draw the Lewis structure. So, you know, there are different kinds of rings that occur in Kelvin. And so the Lewis structure, we just care about the linkages like this. And so a whole bunch of these CH2s linked together. CH3s are called methyls. CH2s have a name too in organic chemistry. In organic chemistry, we call CH2s methylenes. So there's a whole bunch of methylenes linked together like this. You don't need to know methylene, but you should know methyl. Well, what do people do when they want to zigzag this? When people want to zigzag this, they draw it like this. You get practice doing this in organic chemistry. We don't show the carbon atoms because things can get a bit messy. This is called a chair. And so this is the zigzag pattern of the ring. Chair. And then you get practice. In organic chemistry, you practice drawing these. You know, one goes straight up. Each one of these has one going straight up. And then one goes down. So you practice these. I'll just show you what it looks like. So we try to visualize things, chair conformation. You can see people practice. It's quite a lot. They try to get good at drawing chairs. Right here. It's a pretty good one. It doesn't really show the wedges and the dashes. This is called cyclohexane. It's a ring. Okay. Draw Lewis diagrams for these 5 acids of bromine. HBr, HBrO, HBrO2, HBrO3, HBrO4. Okay, is it here? All right, why don't you try drawing the Lewis diagrams for these here?